Hi, welcome back to Verilog Fundamentals. You're learning the most popular hardware description language, Verilog. In this module, you'll see one of the key things that makes Verilog, Verilog. Modules. Modules are an important aspect of the language because they allow you to break up complicated designs into simpler components. After you define a module, you can create as many instances of it as you want. You can even reuse module definitions in other designs. To work with modules, you'll need to define how the inside of the module works. This requires that you declare a module with a module keyword. You'll write the word module, the name of it, and end it with a semicolon. At the end of your module, you will write the end module keyword and a trailing semicolon, which people from other languages often forget. So just please don't forget the trailing semicolon. Inside the module, you can code it up line by line and describe what this module can do. You can create wires and registers and add whatever operations you want. Once you have a module, then declaring instances of it is as simple as declaring a wire or declaring one of the Verilog logic primitives, except you're going to be writing the name of your module instead. You can create as many instances as you want, and your module definition is going to be used to create multiple clones of your actual module in the design. Once you have an instance of your module, you're going to be able to connect it up to the design by using ports. Let me show you in code. Module, my module. That's the start of declaring a module called my module. Notice we have an open parenthesis. That's the start of the port list. Then I'm going to list the inputs and output ports. This is specifically in the ANSI C-style port declaration, and it's also my personal preference. This is the primary way our module is going to communicate with the outside world. There are ways to reference items in the modules above it, but I would recommend not reaching for those features. We should design our modules so that we can easily reuse them and multiple projects. So just stick to using ports. Inside the module, you can do anything you like. This is going to be where you define what this module actually does when it is instantiated in the design. Here, I gave my module a register, and I decided to capture the value of A into a single bit register. The world outside my module doesn't know and doesn't care about what I do inside my module. They simply want to give input and receive output from my module. I have total freedom to declare whatever I want in order to get my job done inside this module. Of course, at some point, it would be great if I supplied my results on the output signals. In this case, we are going to be doing something very simple and performing a logical AND on the input signals. The outputs are how we are going to send that information to the outside world. Finally, we end our module. Notice that the end module keyword does not end with a semicolon. Also notice that this is a module definition. We haven't actually had it created in our design yet. This code simply explains to the compiler how our module is to be defined when we do try to create one, but we haven't actually told the compiler to create one yet. Finally, another thing to note is that you cannot try to declare a module inside a module declaration. Every module needs to be complete and standalone. Be careful with what I just said. I said that you cannot declare a module inside a module declaration. You can create module instances inside your module. You just can't start defining another module until you're finished defining the one you're currently writing. With a module like that in existence, when you want to work with it, the first thing that you need to do is include the file that declared it. By convention, the module is usually in its own .v file. You need to include the module file in all the files that want to use that module. Also, every project needs to contain a top-level module. This module cannot be instantiated by other modules in the model. And what I'm trying to say is, this is a module that is not going to be called inside other modules. This one is at the top of the hierarchy. And oftentimes we simply call it top, meaning that it's at the top of the hierarchy. And since we're not going to be declaring it in other modules, we can declare it without any ports. Inside the top level module, we see that the signals are declared and initialized with values. Finally, we can start to add our components together in the top level module. You just need to say the name of the module that you want to instantiate, and then give the instance a unique name. And then you have to supply signals to the port list. Not all languages have this separation of declaration and definition that Verilog has. The main advantage is that it makes code easier to share across projects. Basically, when you declare a module and code up what it can do, you are reassuring the compiler that this module exists, and the compiler will be okay with compiling code that tries to instantiate this module. All you need to do is define the module once in one file, and then you're free to use it everywhere else in all your other modules and in all the rest of your project. If you ever need to change or modify how the module works, you only need to do so from one file. As a convenience, all the include compiler directive does is it literally pastes the code into the file where we are compiling. It is just a convenience and you don't have to use it. Another way is to simply supply command line arguments to the compiler in order to tell it where to look for our modules. However, using the include directive is what we typically do. There's also some fancy tools out there that allow you to, quote-unquote, go to definition of a module. But they only work if you're actually using the include directive, because it relies on parsing the code. In Verilog, it is actually legal to decide that you want to use a module, but you're not going to bother with connecting up every single port that it has on its port list. This might seem like an unimportant thing right now, but as you'll soon see, there are modules that can contain hundreds of ports, and it would be a tedious task to go and try to connect them all up when you really only need to connect up a couple. Let me show you in the form of a diagram. I have one file called top. This file is going to contain our top level module and is going to be at the top of the design hierarchy. Suppose that you write a module that implements a decoder for a 7-segment display. All you would simply need to do is include that module in your project, and you can start using the decoder in your top-level design. Then, maybe you implement an analog to digital converter module, and maybe that module is using another module that abstracts the interface to using a specific ADC chip. You could code this up here and invest all that time to make it work, and you're going to be allowed to copy these files into your other designs and your other projects and start using them there as well. Here's the code you saw in the slides. It declares a module called myModule. We have a port list here with 2 inputs. These are both single bit nets and 1 output. Inside, we're declaring a register, and we're setting it equal to A. This is just to demonstrate that we could really do anything we want in here. And the outside world outside this module isn't going to worry about how we get our job done inside here. It's only caring about what it connects to on the ports. And then down here, this is where we actually compute a output for Y. In the same folder, I have this file called top, and you'll notice up here at the top I have my include compiler directive commented out. I just want to demonstrate to you that we're trying to use our module here, but the compiler needs some way to figure out what is this module. And just as a reminder, I'm using this task runner extension, which is reading our tasks.json file inside this .vs code file. If I look inside here, the build task is simply going to call Icarus Verilog, and it's going to compile our top.v file here and create an a.out. So let me delete a.out here, and we'll go to top.v, and I'll click build, and it's going to fail, saying it could not find the reference to my module. Well, that's because we have it commented out up here. All I need to simply do is uncomment this by hitting Control/ and save it. And now when I build this, we get the check mark. It's successful. And I can run this, but there's not going to be any output from running it. This module doesn't have any display system tasks, or it's not generating a dump file. Another thing to be aware of is I can create multiple my modules. And I can give them each their own signal. Oh, whoops. Go. Oh, well, we're about to fix that. That warning is gone. And I can build this, and everything is working as expected. In that demo, I made some instances of a module, U1 and U2. Each instance you create has its own copy of the module. They each have their own set of ports and their own separate set of nets and registers inside. You declare them the same way you might declare a primitive logic gate, and also sort of like how we declare wires and registers. Speaking of which, Verilog does allow you to declare an array of instances in the same way that you would declare an array of a net, by simply putting square brackets with a range inside it. We'll see this in an upcoming example. Verilog allows you to make your module declarations more flexible by using parameters. Parameters can be set with default values, but when you use them, it allows users of the module to change the size of things. This happens when the module is actually instantiated and the programmer decides to override default values provided in the module. An example of this might be, maybe they want a bigger or smaller memory size for a data buffer when they use your module. The local param also defines a constant in the same way as the parameter, except for one thing. This one blocks users from changing its value, and these two constructs can be used together to help other programmers know what they can change and what they need to leave alone. An example of this in action might be something like the state encoding of a finite state machine. You wouldn't necessarily want that to be customized in your module, and so you would use local param. Ultimately, the best module declarations are ones that won't lead programmers to try to go in, open up the file that the module is contained in, and change how the module was declared. They should be able to get what they need just by instantiating it in their module. Let's make some changes to our design. First, let's start by talking about parameters. So if I come back over to how my module is defined, I can simply create a parameter, and I'm getting some nice autocompletes here. So I'll go ahead and accept this autocomplete. And I'm going to make an ID number. So I'm just going to call it ID num, and we'll give it a default value of 0. And I'm using tab to step to each complete field on this code snippet here. The The next thing I want to do is I want to add a display task to actually print out the ID number of this module. Is equal to %d have ID number semicolon. Let's go ahead and save that. Oh, forgot the comma. Save that. Okay, this is looking good. So now we've defined a default value and we've added a display task. Let's go back to top and we have 3 modules here. Let's try to change what they are set to. So for u2 dot ID num, we're going to set that equal to 2. And we'll do the same thing for 3. And then 1 will keep the default. Oops, forgetting the keyword def param. This is actually going to allow us to access that parameter. Save, there we go. So let me get my task and build, and we successfully built. Let's go ahead and run it. And we can see that U1 printed out 0, U2 printed out 2, and U3 printed out 3. And that's because of our def params up here. Excellent. Now let's add a local param. And let's call this version, so maybe like a version indicator, and let's call it version 2. And let's update our display task to actually display that. All right, and we'll come back over here and let's try to change that local param. We shouldn't be able to do this. Let's say version 4 and save that. And we're already getting a problem. Attempted parameter setting of non-parameter param version of U2. It's saying we can't do that. So let's go ahead and take that off. Well, we'll leave it there and comment it out. Save, build, and run. And we can see that version 2 is there. And if we are using that in multiple spots, or let's say we're calling other modules that use the version, we only need to update this in one spot in order to change it everywhere else that that parameter is referenced in our module. The other thing I want to show you is that it is possible to make vectors of instances of modules. So in this case, I'm going to make 4 here. And as soon as I save that, Verilator is going to complain that I'm driving Z3 with 4 different signals all into one wire. But that's okay, we'll just ignore that for now. And another thing that's tricky, but something to pay attention to, if I access index 0 of U3, so I'm getting just 1 of the 4 on U3, and I set the ID number to 99, Verilator is going to complain, and Verilator doesn't support this. It doesn't know what you mean when you access index 0. But check this out. Icarus Verilog, which is only a simulator for the Verilog language, it will build this, and if I run it, it works as intended. So just something to be aware of. Verilator is it's acting as a linter right now, but not everything that you can do in the language is supported by each compiler. That's something to be on the lookout for. This module got you using modules in Verilog, which is at the core of the language. You declare a module to teach the compiler that this module exists, and here is how it works. Then, you can declare an actual instance of a module. It's just like declaring any other variable or function. Parameters offer more flexibility to module definitions. You can allow someone to more easily modify something that they may want to change in the module. Local params allow you to express in your code that something shouldn't be changed or modified in the module. Modules allow us to define our design in chunks and build up a hierarchy of components. They're also reusable across projects, and this is important in order to make sure that we make the most of our investment.